Hi, and welcome back to another supervised learning lecture. In last week's lectures, we thoroughly explored linear regression as a way of predicting real-valued responses which take values anywhere on the number line, based on a collection of covariate or predictor values. What if instead we wanted to predict a binary outcome? For example, what if we want to predict whether an image was of a cat or of a dog? Or in a more serious example, if we wanted to use birth weight to predict whether or not an infant would survive, to predict infant mortality. In these cases, we have an outcome that doesn't just take any old real value, but specifically must take either the value 0 or the value 1 in its encoded form. Is it still possible for us to use the standard linear regression techniques that we've developed already in cases like this? That's exactly what we're going to investigate in this video. So before we get started, it's important to make a brief aside on nomenclature. Typically, we're going to encode yi as 1 if an event happens, and yi as 0 if an event does not. And the 1s are generally referred to in a statistical context as successes, while the 0s are referred to as failures. This, however, can be a bit misleading because successes don't always correspond to a positive outcome. For example, if we were considering infant mortality, then we clearly don't want to refer to a child death as a success. This language is inherited from considering binary responses as realizations of Bernoulli random variables, but must be used with care. While those within the statistical and data science communities are likely accustomed to this terminology, specialists and practitioners from other subjects often aren't. So let's focus in on our infant mortality example and consider what might go wrong if we directly apply a linear regression model fitted by least squares to these binary outcomes. Firstly, we can see that we don't get a predicted value of 0 or 1 for any of these points, as shown by the blue line here. We get a predicted value that is usually between 0 and 1. It's tempting to interpret this as a probability, but is that actually a valid thing to do? Is this truly a probability? And if so, what is it the probability of exactly? In this case, we can say yes, this is an estimate of a probability, and specifically it's the probability of mortality given birth weight. But we have to be careful when we don't have complementary events as our outcomes here. If we'd instead had an image classifier separating those cats and dogs, we would estimate the probability of a cat, for example, given the image and that we know that the image is either a cat or a dog. We don't have a dichotomous outcome here, and this probability doesn't match up with what we're really interested in, which is the probability of a cat label given the particular image. This is a subtle but important distinction to make when your two events aren't complementary and don't cover the entire field of possibilities. So we've established that our linear model here is returning probabilities rather than 0-1 values. This is known as a soft or a fuzzy prediction, rather than the hard predictions that you would use to construct a confusion matrix, where each outcome has a binary prediction of 0 or 1. We can convert these soft predictions into hard predictions by setting a decision boundary. This is the level at which we would decide to predict a 1 or to predict a 0. So, for example, we might predict a death whenever our output is greater than 0.5 here, but notice that there's no reason why we have to choose 0.5 as our boundary value. We could equally have picked any other value between 0 and 1 as our cutoff if we didn't consider false positives and false negatives to be equally consequential in this context, and this is something that we've already considered within the ethics course. We should note that by setting this decision boundary and making hard predictions, we're losing some of the nuance from our model. We're going from a probabilistic statement about our expected outcome to a deterministic statement. How much nuance we're going to lose is going to depend on how closely our predicted probability was to either 0 or 1, where we're going to lose the most nuance when our predicted probability was close to 0.5. These two types of prediction, soft and hard, give us two obvious approaches to estimating the linear regression coefficients, here by least squares. We can minimize the squared prediction error on either the binary or the probabilistic predictions. Whichever we choose, we're going to run into a major issue here. You've probably spotted already, I'm sure you have. The issue here is that our predicted probability is not always in the range from 0 to 1. If the birth weight is low enough, we end up with a probability that's greater than 1, and if it's high enough, it's going to be less than 0. So our probability can't be interpreted as a probability at all. This same problem is going to occur whenever you try to apply linear regression directly to model binary data. If you extrapolate far enough, your model is going to break down in this way. So to get some inspiration for how we might address this issue, let's consider our linear regression model once more. In linear regression, we model the observed outcome as normal random variates, while their expected value is going to depend on the linear combination of our covariate values as given here. When we have binary outcome data, we can consider instead the observed outcomes as being Bernoulli random variables, and letting the expected values of those depend on the covariates, similarly to how we did before. What we need to note here, though, is that our Bernoulli parameter theta is a function of the covariates, and unlike for Gaussian random variables, this parameter is also going to determine the variance of our responses, so we don't have an equivalent of our theta term here. Our betas control both the mean and the variance. Since the parameter theta represents the probability that each outcome takes the value 1, we need to construct our function g that links the linear combination of covariates to the parameter value to ensure that the resulting value of theta is always going to be between 0 and 1, no matter what the value of our covariates. Have a think and see if you can come up with some candidate functions that might work here. So it turns out there are very many, and in fact infinitely many, such functions that you could use to map between the reals and the interval 0, 1. In particular, what this means is that we could use any cumulative density function in place of g here. And even more specifically, we might use the CDF of a standard Gaussian random variable to link our Bernoulli parameter and a linear combination of covariate values, as is shown in the first line here. This leads to a model called probit regression, where this strange name comes from a portmanteau of the two words probability and unit. I'm mentioning it explicitly here because it's often used instead of its close neighbour, logistic regression, and it's logistic regression that we're going to focus on for the rest of this video. In a logistic regression, it's the logistic or sigmoid function that's used to link the Bernoulli parameter and a linear combination of the covariates, as shown in the second equation. This choice of g might seem a bit strange and a bit convoluted, but actually comes from a similar idea to the probit regression, where instead of using a normal distribution, we're using what is known as a logistic distribution, and this is where it gets its name of logistic regression. Additionally, what we'll see if we do a bit of algebraic manipulation, which you'll get to do for yourself in the lab this week, is discover that this logistic regression model uses a linear function to model how the log odds of a success changes with each covariate. And for those of you not familiar with odds, they just give us another way of expressing probabilities in which addition and multiplication are the key operations rather than multiplication and exponentiation. And they're very often used in a gambling context because they give an easy interpretation of whether or not a bet is good to take. So on this next slide we can see a definition of what the odds are. The odds of an event A is simply the probability of that event happening divided by the probability of that event not happening. Odds values therefore take non-negative values, and values greater than 1 are going to indicate that something is more likely to happen than not to happen. Our model parameters beta within a logistic regression then tell us by how much the log odds of a successful outcome change per unit change in each covariate. Equivalently, e to the power of that coefficient is going to give us the factor by which our odds of a success are going to change with each unit change in the corresponding covariate. Again, this is something that you'll see for yourself during this week's lab, and you should note in particular that the coefficients do not give the change in probability of a success. The change in probability is going to depend both on the current value of the covariate as well as the change in that value. So what happens if we apply this logistic regression model to our infant mortality data? Let's have a look. When we apply the model, we end up with predictions that are always going to be between 0 and 1 by design, and which can be correctly interpreted as the probability of infant mortality conditional on the given birth weight. The S-shaped curve that we see here, though actually it's been reflected here so it looks more like a Z shape, is known as a sigmoid function, and it's characteristic of a logistic regression. We've engineered this property into our model so that no matter how low or how high our covariates become, we're always going to yield a prediction that is a valid probability here. We've successfully adapted our linear regression model in order to model these binary outcomes. So in this video, we've introduced our first adaptation of the linear regression model, and in particular, we've done that in order to extend it from modelling real-valued outcomes to binary-valued outcomes, so it can be used for a two-class classification problem, and we can use our linear regression model now in new data settings. In particular, we described our binary outcomes as Bernoulli random variables, and used the logistic function to link our Bernoulli parameter theta to the linear combination of covariate values that we're already familiar with. We've briefly alluded here to how we can estimate and interpret the model parameters beta, which we'll tackle in greater depth in the coming videos. In the next of these, we're going to consider how we can use the method of maximum likelihood to estimate these regression parameters, and also quantify our uncertainty about these estimates. Thank you very much for your attention, and I look forward to seeing you in the next video.